So today we are going to talk about our new project. The first time we're going to have done, we'll do regression, because up until now we've been doing classification. So this is going to be regression, so that's a bit different than what we've done before. And the last project is going to be multi-class classification. So we're going to be have 43 classes in the next problem. Okay. This one's going to be regression, and this is a problem that was inspired by the aerial robotics competition this summer, where there's these little Roombas that are driving around, and they have this little flap here has a spring under it, and when you press it down, it makes a switch. It presses a switch, and so the idea is you have a drone flying around, and you have to herd these Roombas and try to get them to go outside over a certain line. They go around randomly. And when you land on them, they'll move for a certain amount of time in the direction that they're pointing when you land on them. Okay? And so you need to identify where they are, first of all, in general, but then once you get to it and are like hovering over it, you need to know in which direction is it pointing, so when you land on it, where it's going to go. Okay? So that's the main problem. And I was like, well, that's a cool problem we could solve. You know, this is a regression task. We need to know in which direction is this pointing. You know, angle from 0 to 360 degrees. It's not just, is it a Roomba or is it not a Roomba? Okay? So that's the problem that we're going to solve. And we're going to do this with artificial neural networks, okay? Which is something that I've been working with for many, many years. It's my PhD dissertation on that. So, you know, we finally get to all the stuff that I've been working a lot with. And recently I've been working with the convolutional neural networks, which is the next project we'll do. So this is, you know, really near and dear. So I was able to really put together a good description for these neural networks. And, you know, traditionally, this type of a lecture is going to start off where you talk about the biological neural network, and then show how what we do in these artificial neural networks is built on that. I've actually decided to turn this lecture on its head and do the biological part at the end of the lecture, okay? And instead build it from mathematics, okay? To show you, because if you jump straight into that, and I jump straight into all the matrix notation and all the things, it's so complicated that you're just going to lose perspective. And what I've done here is to build very progressively and add on a little piece at a time and add on a little piece at a time so you can really understand what's going on with these neural networks. Okay? So I've never tried to teach it in this way before, and hopefully it'll help you to, you know, understand the details of what's going on, especially once you get to the end and there's all these matrices and matrix multiplication that gets really complicated. Okay? So I'm going to start off with a very simple problem. Okay? Here we've got a bunch of data. Okay? We've got, 10 data points, I think it is, a bunch of X's and a bunch of Y's. Okay? And we want to come up with an equation that fits this data. Okay, basically it comes down to here, it's bitty linear regression. Okay, so of course I'm going to be doing all this complicated stuff, and like I should just use polyfit and I'm done. So bear with me. Okay, I'm going to eventually move beyond where polyfit is going to be useful. Okay, so if I have this sort of system, we can think about having my input X and I multiply it by some constant, W, and get an output. That's basically M times X times M, okay? And in this problem, you can see these points go through the origin, so we'll get to this in a minute where there's a y-intercept. But let's, come about the idea, well, let's just try and come up with what is the best W that solves this problem, okay? So our output is going to be, output of this neural network, call it N. We're going to take our input X and multiply it by some constant W, okay, and get an output, okay? And so if I guess some random W, that's going to give me some random slope, and maybe it looks like this, okay? And so then I need to have a way, well, how do I pick a better W than this random one that I picked, okay? So what we can do is we can look at a measurement of the error. So for every one of these points, let's take the difference between the real position of the point, the yi, and the predicted position of the point, which is the w times the xi. Okay? For each of however many i's there are. I guess there's 10 in this case. Okay? You add up all of the errors, and that will give you an error. Now, in this case, the error will be greater than 0 because the yi's are larger than the wx's. So when I subtract them, I get a positive number. So I get a positive error, and that means, well, my slope is too low. If I have a positive error, then I should increase my slope. Okay? So I'm going to introduce this thing called a learning rule. Okay? And in terms of the notation, this superscript that I put in parentheses, that's a time step. So this is whatever my current weight is, and this is going to be the next weight, okay, in a time series. All right? So I'm going to use the current weights, find the error in the current weights, and I'm going to multiply it by some number mu. And eventually we'll talk about this more. It's called the learning rate. Okay? And basically, if the error is too big, let's say that error ends up being 100. Okay? Then I'm going to add 100 to the slope, and obviously the slope's going to get way too big. So I might have mu be some small fraction of a number to make sure that that doesn't add too much to the error. So I can make mu quite small, and then I'll make very small changes to W. W just change a small amount. Okay? And there'll be conversion issues and that sort of thing with this, but we'll talk about that some more later. So mu is just some relatively small number to make this happen in small bytes. Okay? So we've got some code. Okay, let me go ahead and get out of here, and I'll run this code for you. Okay? And so this code is uploaded to D2L. There's a whole, what is going on? Why is that looking weird? Did I not cancel this? Why? You see that? Do you see that yellow line? You kind of see it around the edge. I don't know why that's there. Hopefully it's recording. Well, that light is blinking. I dare not click on it because that will pause it. I think it's working right. Anyway, so you have this file. It's got a whole bunch of different parts, and I'm going to be commenting and uncommenting different parts. But here I'm going to start off with this first part here. I've got x as my lin space of values between 0 and 10. Here's my straight line with a slope of 1/2 going through the origin. And then here's a random value for my w. Here's my small mu. Okay? And then I'm going to go through going through my loop here. As long as the error is greater than a very small number, as long as there's still some error, I'm going to continue. Okay, I'm going to calculate the error, the sum of the difference between the y's and the wx's. Okay, I'm going to increase my w by mu times whatever the error is, and then I'm going to plot some stuff. And I keep doing that over and over and over again until the error becomes less than 1 to the -7th. Hit play. Okay, the window's back here. Can't see it. Here's the window. Let me stop it and run it again so we can start from the beginning. So it starts off at some random slope, and it gets closer and closer and closer. Okay, and here you can see the slope. I'm displaying on the screen the slope. We know the actual slope is 1/2. After 67 iterations, it finally gets the slope to within 1 to the -7th of the actual value. He's like, big whoop, I can do this with polyfit. Okay, but you see it's working. Okay. All right, so then we can talk about solving a harder problem, okay? And that harder problem is where the line doesn't go through the origin, okay? So if I have this as my model, just w times x, my line is always going to go through the origin, and the only thing I can ever change is the slope, and it'll never get very good. Okay, so up here, rather than just taking x times w, I'm going to add in a w0, I'll call it. Okay, and I'm going to sum them together. So this is just basically mx plus b, where the m I've called w1 and the b I've called w0, and it'll become more obvious why I'm calling these w's later. Just change the variable names, okay? And you can see I'm building a visual representation of what that equation is, and this visual representation will become more and more complicated as we get more and more like a neural network, okay? So I'm still going to use a similar error. It's just I'm going to see what is the actual value minus the predicted value. Okay, and I'm going to need a learning rule for how to change W1, which was my old W, and I'm going to use the same learning rule for W0. I'm just going to say, how much is the error, and I'm going to add that error to the W0. Okay, and here's the code. It doesn't look much different. Okay? Now, if we go back to code, and I comment out the first part here, and uncomment the second part, pull up our figure, and we run this. Okay, you can see it's displaying the slope and the the slope and the y-intercept. I think it's in that order. Yeah, W1 and 0. Okay, and it changed it. You can see they both changed. The actual value, it should have a 0.3 slope and a 1 value for the y-intercept. And it actually ended where the error was 0. Okay. Now there's two things going on here. Okay. One of them is that basically it got it to where the errors on one side are positive and the errors on the other side are negative, and they've canceled each other out and gotten a 0 error. So that's one piece that's going on. Okay. But you know, there's a way we can kind of sort of fix that kind of in a way. Okay, so essentially what we end up with is we end up with a situation where you know, we don't quite get what we want. Now, a way that we can fix that, is by noticing something that with our line here, you know, basically, I mean, in the end, the main reason is that we got positive and negative things canceling out, and we could put an absolute value in there, and it might work some things out. But I'm trying to go towards a specific goal, and I'll show you another way rather than the absolute value to fix that. And one is to notice that, you know, if I've got a line, the higher I get in an x value, the larger the error is going to be. Okay, and if we emphasize that even more, that at larger values of x, that should play a larger role in making the slope adjust. Okay, because that's the main thing, you know, as we get, if it's diverging there at large x's, it's because the slope isn't right, not because the y-intercept's not right. So if at larger values of x, we say that we want the error there to play a larger role than what it currently is, what we can do is we can put in here that we take the error and we multiply it by whatever the x value is. So as x gets bigger, it adds more to the error than it would for a smaller x. Okay? And then we can put that in our code. We just put the x, you know, that extra x times in there, and that's really the only difference. So if we go to our code again and we comment out this piece and we comment in this piece, pull up our figure, and we run this, and you can see it bounces around. You see that it bounced around a little bit, and we can actually get rid of that by lowering the mu. If we make the mu smaller, it will not bounce around as much, but it actually will take longer because you're taking smaller steps. Okay, and you can see we're getting closer. You know, the slope is supposed to be 0.3 and the y-intercept is supposed to be 1. And you know, we can, if we wait long enough, it'll get close enough and it will stop. Okay, so we're now able to, you know, basically perfectly do a get this model to fit for a straight line. Okay, now we're going to look at this in a more sort of rigorous way. We're going to end up with the same learning rules, okay? Because the learning rule is, you'll remember, we added this little x piece for the slope. W1's the slope. So for the slope, I've got that extra x piece in there, and I didn't need it for the b because it doesn't diverge because of b, it diverges because of m, okay? Now, I changed one thing, and I put a squared on here, okay? And this is one way that we can get rid of that problem with the signs, because when I square it, negative errors will turn into positive things. So we fixed that one problem that we kind of already knew was there, that the positive and negative errors were canceling. So we fixed that by squaring the error, okay? And what we then have, and this is, in terms of terminology, this is called a sum squared error. where I square the error and I sum it. And it's a very common thing in machine learning to talk about sum squared errors. Now, I've squared that, but I haven't changed the learning rules. And what we're going to find is that a more rigorous way of looking at changing, updating the weights is going to lead us to these same update rules that intuitively we have an understanding for why they should work. Okay? So, what we're going to look at in the end is that we have two parameters we're trying to adjust. We're trying to adjust W1, and we're trying to adjust W0, trying to adjust the slope and the y-intercept to get the right slope for these things. Okay? And so the way we can look at it is, if we change the slope, how much does the error change? Does the error get worse? Does the error get better? We want to change the slope so that the error gets better, that the error becomes less. Okay? So we can look at the partial derivative of the error with respect to the slope and the y-intercept. Okay? So conceptually, that's easy to understand. You know, basically we have this box and we've got dials on here for the slope and the y-intercept. And the output of the box is telling me the error. And so as I turn these dials, I want to change that error so the error gets as small as I possibly can. And so in order to know, should I turn this dial this way or should I turn it that way? Well, I turn it a little bit that way, and if the error increases, I know that's the wrong way to do it. I should turn it a little bit the other way. And that's what this partial derivative is going to tell us. Now, the error equation is a nice explicit equation. It's you know, it's all there. If I know what my W1 and W0 are, I can get the error, so I can calculate the derivative of the error. Okay? And it's actually not that hard, okay, in this simple case. So if I wanted to find what is the derivative of the error with respect to W0, I got to do a little u substitution because of the squared thing. The 2 comes down out front, and then this thing is there with an exponent of 1. And then I need to take what is the derivative of the thing inside with respect to W0. And the derivative inside with respect to W0 is -1. You see that? Okay? And so this is the derivative of the error with respect to W0. Okay? And you can rearrange it. The -2 thing can come outside the summation sign. And you'll notice that that part is exactly the same as our update rule. Okay? Now mu is a small number, so you know that mu is a sort of an arbitrary number, so we could kind of lump that -2 inside that mu. Okay? But what's important is that there's the main piece there. Then if we take W1, we take the derivative of this with respect to W1, the 2 comes down out front, this thing there is still to the first power, and then I need to find the derivative of the thing inside with respect to W1. And that's not just -1, but negative times xi. Okay? Now one of the weird things to think here is that W1 and W0 are our independent variables. Those are the things that we're considering changing. Okay? The x's and the y's are essentially constants. Okay? My training data determines what the x's and y's are, and they don't change. I collect my training data, the x's and the y's are fixed. So they're essentially constants in this whole problem, and the things I'm changing are the W1 and the W0. Okay? So, the derivative of the error with respect to W1 turns out to that, and lo and behold, there's that x in there again. Okay? So what we're going to do is look at, does the error increase or does the error decrease for each of these? And I want to move in the direction of a decreasing error. So I'm going to write my update rules, my learning rules, in a different way, but is exactly the same as what we had before. Okay? I'm going to multiply mu times the derivative of the error with respect to W1. Okay? Now, there's a minus sign there because I want to move in the direction of decreasing error. Okay? So if increasing W increases the error, then dE dW will be positive. So I want to go in the other direction. That's why there's a minus sign. Okay? So you see here, there's no x. This is kind of weird. There's an x on the W1 term and no x on the W0 term. Okay? Here, you don't see that discrepancy. It's the same thing. I just take what is the derivative of the error with respect to that term, and that's what drives my decision for whether I increase or decrease, and by how much. Because if that derivative is very big, man, I get a lot of bang for my buck. If I change W and the error decreases a lot, hey, I should change that one a lot more than the others, because that's how I'm going to get a bigger effect for my error. Okay? Now, this concept is called gradient descent. Okay? And here's the error description. There's the learning rule now rewritten with the derivatives in there. Okay? And like I said, the x's and the y's are constant. They're determined by the training data. So what we can do is we can draw our error surface, or our error function. Okay? This error function essentially depends on two variables, the W0 and the W1, the slope and the y-intercept. Okay? And so I can visualize this. This is a three-dimensional problem. The error is the third dimension. The W0 and the W1 are my x's and y's. Okay? Now, this particular drawing does not have anything to do with this problem. It's just sort of a general thing. I mean, that shape is gonna, who knows what it's gonna look like? But you could plot it. For all different W0s and W1s, you could plot it. Okay? And it would have some sort of surface. And in general, these surfaces can have all sorts of different shapes to them and different qualities to different places. Okay? What I've done here is I've drawn the surface map and then the contour map below. So this is sort of like if you're going hiking on a mountain, and those are lines of constant elevation or lines of constant error. Okay? So that's, a different way of visualizing the surface in 2 dimensions rather than in 3. Okay? So you can have plateaus where it's flat and there's basically no lines. Okay? Nice and flat. Okay? If you're in this portion and you're using the gradient to drive you, it's flat. The gradient's basically 0, so my weights are not going to change. So if I end up in a plateau where there's no gradient, then my weights will never change and I'll always stay there forever. Now, if there's a slight incline, it might take me a long time to eventually get down there, but it's going to be a while. Okay? We've got a saddle point, and the saddle point basically determines if I'm on one side of the saddle point, I'm closer to this, I'll fall this way. If I'm on the other saddle point, I'll fall that way, which leads us to this point that we might have local minima. Okay? We might have a valley in our mountain, but that's not sea level. I have to come up over a hill and then go down, and eventually I get down to sea level. Okay? So I'll have local maxima and I will have global maxima. Okay? And this right here is the #1 reason that gives critics ammunition against artificial neural networks. And that is that our neural network can get stuck in these local minima. If I'm following a gradient descent where I'm going down the hill, if I get to a local minima, all of the gradients, if I move in any direction, it brings me back to where I am, and I'll never get out. I'm trapped. Okay? Now, in 2 dimensions, we can plot this and look and see, oh, where is the global minima? Oh, that's the value of W0 and W1 I want to have. But imagine this is a space where you have thousands even. You can't visualize that. It's very hard to find the global minimum. Okay? So we have to keep that in mind. Now, to visualize this a little bit more with the gradient, I'm kind of sort of zooming in where this global minimum for my error is. And I draw the contours around that with W0 and W1. Okay? So let's say I randomly choose a W0 and W1 and I end up at that point in the space of these W0s and W1. Okay? Essentially, by calculating how much the error changes when I change W0 and how much the error changes when I change in W1 will give me an arrow that essentially points in the steepest uphill direction from there. Okay? And we'll talk soon a little bit about this notation of writing this as a gradient. But essentially, we're looking at, how if I change W, either W0 or W1, is E going to go up or down? Okay? And essentially, this is going to tell us which direction is in the direction of maximum increasing WE. So I want to go the other way, some small amount. Then once I move some small amount, I recalculate the derivatives, and they'll point in a different direction. And I'm going to move in that opposite direction again. Recalculate. Move, recalculate, move, recalculate, move, recalculate, move, recalculate, move, recalculate, move, recalculate, move, recalculate. And every time the error is pointing in a different direction. And eventually I get to the point where the error, the change in the error is 0. The derivative of error is 0 because I'm at that minimum. Okay? And so essentially, this whole process is I started off here at some random place, and what it does is basically I just fall down in that error. I travel downward in that error space until I come to a local minimum. Okay? So that's why they call it gradient descent. I'm descending the mountain in the direction of the highest gradient, the steepest direction. Okay? Now, unfortunately, had I chosen a position over here on the other side of the saddle point, I would have fallen down into the local minimum. I would have gotten relatively low error, but it wouldn't have been the lowest possible error. Okay? Now, there are a whole bunch of very complicated ways that we can overcome these things. We can add something like a momentum. Whereas I'm traveling downhill, I pick up speed depending on how fast I'm going. And when I hit the bottom, even if the gradient is 0, I still have momentum that might carry me up over a hill and get me over that saddle point to go down somewhere else. Okay? So there's all sorts of ways we can change this, but right now we're going to look at the simplest one, which is straight up gradient descent. It may not even be that heading in the steepest direction is the most efficient. I might, if I fall in the steepest direction, I might go down and around, and, I might go down like a funnel or something. And if I just headed straight to the global minimum, it would be faster. Okay? I mean, knowing what that direction is not easy, but there's all sorts. I mean, you could fill a whole semester just on different learning rules for gradient descent variations. But we'll stick to the simple one. But at least the concept of this is pretty straightforward. Okay? All right. Now, as you might suspect, this is starting to get a little ugly with the math, and there's ways that we can tighten it up. Okay, we can use linear algebra and matrices to make this stuff look a little simpler. Okay? So, the first thing we're going to do is we're going to take this intercept, which we usually call it a bias, okay, because it's adding, we're multiplying the inputs by a value, and then we're biasing it by some amount. We're adding something, some fixed value to everything, no matter what x is. So they might be called intercepts, they might be called biases, okay? So we're going to say, well, W1 was multiplied by x, so we're going to multiply something by W0 just to make it be similar. And we can multiply it by 1, okay? So it's as if I have another, now I have a 2-input system. I always pass in 1, and I pass in the x that I really want. Okay? So you can look at it now as a 2-input system where one of the inputs is always 1. Okay? And essentially, now, this makes our output now look more like a matrix, and I can take a vector of x and a vector of w and multiply them together, and so I can have a matrix x multiplied by matrix w, where they're both vectors, and we get this, the matrix multiplication basically does a dot product between the two vectors. Okay? So, in this case, x has to be a row vector and w has to be a column vector in order for that to work out. Okay, so that means now we can write our output very simply like this. We can write our error more simply. Okay, so that makes it, makes it more compact. Okay, now if that brings us sort of back to this idea of this thing as a gradient. Now that w that we were writing as a vector now makes more sense. I'm writing the weights as a vector. These w's, we call them weights oftentimes. Okay, so I have this vector w, okay, w0 and w1, and I can think of that as in a vector where I take the first part in the I direction, the second part in the j direction. Okay, and that is what will bring us directly to the idea of the gradient. Now I write it like this, and that is the way that you're most likely to identify it if you think in terms of differential equations and partial derivatives. Okay, I don't know, have you guys taken, some of you taken diff EQs, do you also write it this way with the upside down triangle? Okay, it depends. Okay, these two things are equivalent, but this is more typical to write a gradient like this. And it's defined as taking the derivative of the error with respect to the first variable in the first direction, the derivative of the error with respect to the second variable in the second direction. And that's how this thing turns into being a vector. And it's going to point in the direction of the highest and steepest change in my error space. Okay? So, now we can write our learning rule even more compactly. It's mu times the gradient of the error. Now, technically, this gradient is in bold, so you can tell that it's a vector, because E itself is a scalar valued function. There's one number. You put in a vector input and you get one number, a scalar output. So you wouldn't in the notation notice that that's a vector, except for that triangle is supposed to be bold. And that's where the vector comes in. Okay? That's sort of an idiosyncrasy. So, how might we go about implementing this gradient descent idea? And what I did is I went, rather than actually calculating the partial derivatives, which I actually already did, okay? But problems we do later are going to be more complicated. Let's see, we still got time. Okay, the later problems are going to be more complicated, so I'm going to use the SymPy, which is actually the Python's copy of MATLAB's symbolic math toolbox. Okay, so they took the symbolic math toolbox and just copied it into SymPy, which is great. So if you know how to use the symbolic math toolbox, you're good to go here. Basically, what we do in here, we've got the same thing, x and y. I get random values for W0 and W1. There's my learning rate, okay? And I'm going to define these symbolic expressions, W0 sim and W1 sim. So they're going to be symbolic, they're going to be mathematical equations, essentially. So W0 and W1 sim are going to be mathematical expressions for W0 and W1. Okay, and I'm going to have a symbolic expression for the error. Okay, and right now it's going to start off at being an equation for the value 0. That's what simplify does, is it takes a number and turns it into an expression, mathematical expression. So the eSim starts out as the mathematical expression equivalent to 0. Okay, then I'm going to loop through all of the different points in my input in my training set, and I'm going to convert to a symbolic expression the constant yi, the constant xi, times the symbolic w's, and square them. So the W0 and W1 are symbolic expressions. The x's and the y's are actual hard-coded numbers. They're constants. Okay, so now I have a symbolic expression in terms of W0 and W1. It doesn't evaluate to anything yet. Okay, then I'm going to actually evaluate the error by subs. Subs is substitute. So I substitute in my random value for W0 for the symbolic value, the random value of W1 for the symbolic value. Now E becomes an actual scalar with a number. Okay, then I want to update W by subtracting mu times dE dW0, and I get that with diff. Diff is the error, the derivative of this with respect to that, and then I need to substitute in the values for W0 and W1 to get an actual number for W0 changing, and I do the same thing for W1. Okay. So I've just implemented, that approach, but having the derivatives being solved symbolically by SymPy rather than me doing it by hand. So I don't have to learn calculus, I just let SymPy do it. Okay? So, well, let me show you how that one works. So now instead of our sort of hard-coded work, we're going to go ahead and do it with the gradient descent. This is the same code that I showed you in the PowerPoint slide. We pull up this guy and we run that, and you can see it takes a little longer because it's slow to do all the symbolic math stuff, but it's getting there. It's getting there slowly. You can see this needs to decrease to be 0.3, and you can see it's getting there slowly, and this needs to increase to get to 1, and it's getting there, and you know, it's just slow because it's a very inefficient way of doing this. Okay, but it'll get there. Okay? All right, so now we've done a gradient, a descent way of solving this problem to get me to regress to a straight line. Big whoop. You know, nothing's ever a straight line, right? So we need to say, well, let's try to do this with a parabola. Okay, let's give it parabola data rather than straight line data. Okay, and of course, it's going to be crap because the model is modeling a straight line, and now I give it a parabola and it's going to give me the best fit straight line. It's like doing polyfit of order 1 on second order stuff. It's not going to look very good. Okay, so what we need to do is basically the same trick that the support vector machines did. The support vector machines had this hyperplane, this linear discriminating plane. Okay? And they needed to find a way to introduce nonlinearity into a system that only dealt with hyperplanes. And they used this kernel trick. So we need to introduce some sort of nonlinearity, but still be able to do w's times x's to keep things simple in terms of the linear algebra of stuff. Okay? So what we are going to do is after we go ahead and do our linear algebra stuff, the w times the x, we're going to come up with this thing called an activation function. So we're going to take x times w and we're going to plug it into some function f. And this function f has two requirements. It must be nonlinear, because if it's a straight line we don't do any good. Okay? It also has to be differentiable. Because if we're going to do gradient descent, it has to be differentiable. We have to be able to take the derivative and it not be infinite. Okay? So, you'll notice here that the symbol that you'll often see is a step function. Okay? And the reason for that is the biological inspiration that we'll eventually get to. Okay? So, we can't do a step function. That's definitely nonlinear for sure. Okay, but we can't do a step function because it has an infinite derivative where it steps. So instead, we're going to use something called a sigmoid function. And the sigmoid essentially simulates a step function. Okay, it goes from being 0 to being 1, but it's smooth, it's differentiable. Okay, now there's lots of different sigmoids. This is what we call the logistic sigmoid, and that's the equation for it, and there's its corresponding plot. There's a tangent sigmoid that does a similar thing. There's different types of sigmoids, but the whole idea is we need to have something that's nonlinear, and again, the inspiration comes from in our brain where either our neurons fire or they don't fire. It's a step function. Okay, so we're trying to get something that's kind of like a step function, but it can be anything. And when we get to the convolutional neural networks, we're going to take this and not use anything at all that even looks like a squashing function. It's going to be something very different. Okay, so we're going to take our x's times w's and put it into this function f. And so our error now is going to compare the function values with the y's. Okay. Now, the learning rule doesn't change. I just need to take the derivative of e with respect to w0 and w1. It's a more complicated thing. I need to use the chain rule because I got the f in there. Okay? But as it turns out, that function doesn't actually have a very nasty derivative. The derivative is relatively straightforward. Okay? But still, we're going to use SymPy to help us not have to worry about the derivatives. Okay, so all we need to do to modify this, the code, is to add in a function. I'm adding in a symbolic function for f and one that just takes in regular numbers. Okay? And then instead of just taking w1 times x plus w0, I need to plug that into the function f. And instead of just taking w1 times the x's and w0, I'm plugging that into the f. Okay? There's one other difference. I've got this x dense versus just the x? Because before, when they were a straight line, I was evaluating at my training points. But since it was a straight line, there was no need to have any extra points in the middle. But now that I have something that is now a non-linear function, I need to look what's happening in between the training points to see what's going on. And that's what the x-dense is. It's more points than just at the training data. Okay? So this code is also in the one that is in there. Okay? Yeah, well, right. Okay, so you could run it, but there's really not much point because it's still crap. Okay? Basically what you end up with is a straight line. Okay? So instead of trying to put just a slope and a y-intercept, a straight line through there, it's trying to fit with that sigmoid, that squashing function. Okay? And you can see here, you can kind of see it. You can see how it's sort of, it squashes between 0 and 1. I mean, that function can only output things between 0 and 1 anyway, right? So it can never output a value that's 25 because it can only go between 0 and 1. Okay? And it can't change its shape. It's going to be that S-like shape. Now, it can flop it can make it be negative, where it can be above 0, be from 0 to -1 or 0 to +1, and it can shift where that transition from 0 to 1 goes, but it can't change itself other than that. Just like the straight line can't change itself beyond what it has. Okay? So essentially it ends up making this basically just like a straight horizontal line. This is even worse than having a value line with a slope. Okay? So what that leads us to is we need more of these things. We need to add together more of these squashing functions to be able to do what we want to do. Okay? So we need to go to multi-node networks and even multi-layer networks. Okay, so that's where, if you ever see the abbreviation MLP, that stands for multi-layer perceptron. Okay, now what we have right here is a single perceptron, and it's based on the idea of a neuron in our brain. Okay, and we're going to add more than one. So now we're going to have 2 perceptrons. Okay. And so each of them is going to have the same input. They're both going to input in the 1 for the bias, and they're both going to input the x. But they're going to be able to have different weights. So basically, each neuron will be able to have its own squashing function that's in its own shifted position. Okay? So now we have 2 of these squashing functions, and we need to be a little more particular about the weights. Now we have 4 weights. And we're going to write them in such a way that makes it easy in linear algebra, where the first subscript is going to say which input it is. So you say, the first, that's 0, that's input, no, the first input. This is 0, that's the first input. Okay? So the first index on W is saying which input am I talking about, that 1 or the x. And the second one here, it's 0 and 0. That has to do with the 0th perceptron. 1 and 1 has to do with the first perceptron. Okay? So I've got these 4 weights. Now, that's not going to be enough, because now I've just got these 2 outputs. What am I going to do with these 2 outputs? They're supposed to give me a single y. So what we're going to do is we're going to add another layer. We're going to take the outputs of those 2 perceptrons and pretend they're the inputs to another perceptron with its own bias. And it's going to have its own weights here, and we're going to call them U instead of W. Okay? So now there's 2 inputs from the 2 neurons and the input because of the bias. We're going to sum them all together and go through some other activation function. Okay? So now we have 2 nodes in our first layer and 1 node in our second layer. Okay, now we numbered the weights that way so that we can now have W be a matrix and X be that row vector, and us take a matrix multiplication, these times that, to give the first value, matrix multiply those times this to get the second value. So we can still take X times W, but that gives us, instead of a single value, 2 values that are the values of both sums. So I can get the values of both sums with a single matrix multiplication if I organize my weights in that way. Okay? Then those values have to be put into my squashing function f. Those f's then are sent to this perceptron. So these f's are now the inputs to the second perceptron with, of course, a 1 in the beginning for the bias. And then there's those 3 weights that are multiplied to get a single scalar sum here that then goes into another function g of that sum b. And then the value g of b is our output. That's the output of our neural network n. Okay? Now we can write that all cleanly this way in terms of matrix. Okay? First I take my x times w, I take the f's, I horizontally concatenate that with a 1, that matrix gets multiplied by the matrix w, and then that gets put in the function g that gives me the n. Okay? So I can write it as this nice explicit equation, but it becomes quite complicated because there's all these things going on in there. Okay? And we have to remember that matrix W, the first index is the input number, the second index is the node number. Okay? And so we have then our learning rule. We need to update our W. The only difference here is I put a subscript for the gradient with respect to W. The gradient and the error with respect to W, that's going to be how much W updates, because I also have to update the U as well. And so I look at the gradient with respect to U for that. Okay? So we'll call that cut that here. Okay? We'll finish this lecture next time. That's actually, I planned that we got 2 days to go over this stuff. And then we'll make this extension of the multi-layer perceptrons and show them. We'll do an example and we'll get ready for doing neural networks. Okay, so we'll see you guys on Wednesday and we'll finish up some stuff on these neural networks.